Okay, hi everybody. Prove convergence or divergence for these series. What that means is, it doesn't mean prove a limiting value, it just means prove if they converge, prove if they diverge, okay? But not actually find its value, like this is equal to pi squared over 6. It's not. Well, maybe it is, I don't know, but I don't think it is. But you don't have to find it. Okay, so let's look at this one. Okay, so n over n to the third looks like 1 over n squared. And we know that this series converges, it's actually equal to pi squared over 6. Now, we don't know, so in other words, we'd like to compare to this convergent series, meaning if we can show that our series is smaller than a convergent, it must converge. Its value might be something else, but... Okay, well, n to the third plus n squared plus 1 is bigger than n to the third. Whenever n is a positive, like 1, 2, 3, 4, 5, so this is valid. So that when we take reciprocals, 1 over these things, then flips, the greater than becomes a less than 1 over n to the third, because a bigger denominator makes a smaller number. A bigger denominator makes a smaller number. Okay. But then, the sum of 1 over n to the third plus n squared plus 1 is smaller than, that's what we're showing, it's smaller than the convergent series sum of 1 over n squared. Right? We even know the value of that series, but we don't need to know that. And so when our series is smaller than a convergent series, hence our series converges also by the comparison test. By the comparison test. Okay. End of proof. Excellent. Let's look at the next one. Here we have this. Let's look here. N to the third is going to be much bigger than n. So in the infinite tail of this series, what's going to matter is this n squared over n to the third, which looks like 1 over n. And so our guess is that, we know that the sum of this, equals infinity. In other words, it diverges. And so our guess is that this series also diverges. Let's see if we can prove that. Well, now look at the denominator is now smaller than n to the third, because we subtracted a positive number, right? N is 1, 2, 3, 4, 5. Well, that implies that 1 over these things is the other direction. Okay. Oops, and we actually needed an n squared in the top of both of these. If the numerator is the same, I don't have to put a 1. I can put the same numerator. And now this one is equal to, 1 over n. Okay, but then our series is bigger than a divergent series. So n squared over n to the third minus n. Our series is bigger than the divergent series, 1 over n. Sum of 1 over n. Hence, our series diverges too. It's bigger than a divergent series. It must diverge by the comparison test. Last example. This is a great example. Now, square roots always confuse me, but let's look at their graph for a moment. Now, square roots do something interesting between 0 and 1. So here's the graph of just the function y equals x. Here's the graph of y equals x squared. And here's the graph of the square root of x. Now, over here between 0 and 1, the square root is actually bigger than x. But over here, in 1 to infinity, the square root is smaller than x, okay? And so, anyway, we look at this and we should just say, it looks like 1 over n, so our guess is that it should diverge because this series diverges. But let's see if that works. So n plus the square root of n, well, is bigger than n, right? We've added a positive number. So then when we flip, we get 1 over is less than 1 over n. So that our series, the sum of 1 over n plus root n, is smaller than the divergent series 1 over n, which does not help us. Okay? Because if we've shown that our series is smaller than a divergent series, that doesn't mean it has to diverge. It could converge. It's just smaller than a divergent series. So this is totally unhelpful. Okay? Then, how will we proceed? Will this series converge? Well, no, our intuition is correct. It should basically diverge, and let's see why. Well, n plus root n is bigger than n, didn't help us, but if it is smaller than something, how about 2n? Notice the square root, x plus root x is going to be smaller than twice n whenever n is, at least greater than 1. I think this is true. Anyway, but if that's true, that implies that 1 over this is greater than we flip. So our series is greater than, now we're in business, greater than a divergent series. The divergent series 1 over, right, this is just twice this thing. Anyway, this clearly diverges, the divergent series there. Hence, our series diverges to, end of proof. Okay. This pink problem, you should really make sure you understand this. It's important so that you see the limitations of the comparison test. Doesn't always necessarily work. Okay.